So for number 4, you've got your polynomial is x cubed minus 5x squared plus 3x plus 7. It asks you to rewrite it centered at 4. So what do we need to do? Yeah, you your Horner's algorithm all the way down till you can't do it anymore. So 1, -5, 3, 7. We'll bring down our 1 and multiply, add down, multiply, add down, multiply, add down. Yeah. Do it again. So multiply, add, multiply, add, if I can add, multiply, add. Whoops, I don't need to go all the way there. What am I doing? Stop here. Sorry. Where we? That's the first one. Stop here. Do it again. Multiply, add, stop here. And then the last one is just the 1, right? These are your coefficients now. So your p of x will be 1 times x minus 4 cubed, because you use that as your first coefficient. Your 7 is times your x minus 4 squared. Your 11 is times x minus 4, and then plus the 3. Remember that the answers to these give you your coefficients for your Taylor series, centered at that particular value. Which is why I said you did part of it in the previous part, right? Because you were trying to figure out this number, right? P prime of 4. That's P of 4, P prime of 4. So it really is that easy. You just pull out those coefficients. That's all you have to do. That looks like a good test problem. Just FYI. That shows how you understand Horner's algorithm, understands what the numbers that you understand what the numbers are that you're getting out of there. You put it in there, and it's quick. Right? That's a good test problem.
Number 5 is a good test
problem. Number 5 is not a good test problem.
I didn't think so.
Yeah. Number 5 is a good problem, good homework problem, good major assessment problem, something outside of class, but not a good test problem. But this is a good test problem. Converting something to machine representation is a good test problem. Maybe not as long as the one that I gave you. They have a lot of digits to it, right? But that's a good test problem. You do something smaller. Other questions? Yeah, there's good homework problems, there's good test problems, right? This is a good test problem. Probably have one of those in a couple of weeks.
Can you go over converting to like number 1, I think it was?
Sure. What's that? Just had the paper. Oh, I see. I covered it up with a different paper. All right. So the number you had was 41,864, and the decimal part was 0.525390625. Right? We have to convert them separately because when we do the whole number part, we have to divide by 2 each time. Do the decimal part, we have to multiply by 2 each time, right? So this one, I'll take this and divide it by 2. And then this will be, I need the decimal, I need the remainder part, right? So I should probably let me escape out of that. Do it this way. I'll do the integer part of this, so it'll lop off the decimal. And then this one I will do this minus 2 times that. And then This is that. And pull this down. Pull this down. One more. There we go. Yeah? Okay. All right, so again, the 4186 part, ooh, hey, 41864 part will be, we read from bottom up, so that'll be 101 000 111 000 1000, and that's base 2. All right, divide by 2, keep track of the remainders. That was what we did in that part. For the other one, we multiply by 2 here, right? And then we need to pick off the whole number part, right? So I'll do this minus, I'm going to do it the other way around. What do I want to do? I want to, brain locked up. I want to pick off the 1. Say that again.
I just did the integer.
Yeah, just do the integer G1. That's right. Sorry. My brain just locked up for a second. All right. This one I want to pick off the decimal part, right? So I want to do this minus that. Then that. And then pull. I don't need these parts down here because it stopped, right? Here. So the decimal part then is we read down. So 1000001101. And that'll be 0 point. And then that's base 2. Yeah. All right. So putting those two together is what gives you your number. All right. So far, so good? This part okay? Okay. What's that? What'd you say?
This is so good.
So good? Yes.
Did you just know how far to pull down the 418641 just till it gets to 1?
Yeah, till it gets down to 1 and then you're done. Yeah. Once you get down to 1, you're done. Yeah. And this one, it's possible. This one I did sums of powers of 2, so it came out nicely. I'll do that on the test too, so it's not a repeat. But it's entirely possible that if this isn't sums of 1 over 2 to the powers, then that's not going to repeat, right? So I can't write it as 1 over 2 plus 1 over 4 plus 1 over 8, some combination of those kind of things. It will keep repeat. It'll repeat eventually, which isn't very nice. I mean, how the machine would handle it is that you only have 23 spots for your mantissa. So once you get to the 23rd spot, you just cut it. You just chop it. All right. So far so good? All right. So the next thing we need to do is write this in basically scientific notation. I need to move, this decimal point would be right here, correct? So I need to move that to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times. So you get 1.01 0001111 000 10001101. Phew, that was a lot of words. Times 2 to the 15th. That's the scientific notation part. Yeah? Okay. This is your mantissa part, but you only get to store 23 digits of those things in single precision. Once you get to the 23rd digit, you would chop it. How many digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 21, 24 digits. If I got it correctly. So when you put it in the machine representation, this one will get chopped. It falls off.
What was the part where we had to do like the exponent?
That's the next part I'm going to do.
Okay.
Yeah.
Okay.
Yeah, I just talked about the, yeah, we have to still deal with the exponent. Yeah. I haven't done that part yet. The uptick here, so chopping off the 1. This part right here is what's going to get stored at the end of your number. Okay. Okay with that part? All right. So then the last part we have to do, like Madeline just asked, was about the exponent. I got to convert the exponent to binary, right? But what do I have to do first before I convert it to binary? Yeah, I got to add 127 to it, right? So we need to convert 142 to binary. So I can do that quickly by just changing the other number to 142. So 142 here, reading again from the bottom, will be 10001110 base 2. Again, the largest exponent we could possibly store is that 254. We don't use all ones for an exponent. That's for special case, right? So I could go up to 254. But we do store 8 bits here, right? Now this one has all 8. If this had stopped before, if you had 7 bits, then you would fill with a 0 in the front. If you had 6 bits, you would fill with 2 zeros in the front. You're going to use all 8 bits for the exponent. All right, so then finally, this is how you can, so we got the mantissa part. Again, we'll chop off that. Here's the exponent part. That'll go in front of the mantissa part. One more piece. What's the first bit? A sign bit, and we use which one for positive? 0. Yeah. So if you do our machine representation, then 0, 1, 0, 0, 0, 1, 1, 1, 0. That's the first part. And then that big long thing. That would be our machine representation at that point. Lots of zeros and ones. And there should be 32 bits there for single precision. Double precision jumps it up to 64. And you get 52 for the mantissa, and then whatever that's left, 11 for the exponent. You get 1 for the 52 for the mantissa, 1 for the sine, which gives you the 53, so it leaves you 11 for the exponent at that point. The 142. So remember, not using all zeros and not using all ones for the exponent allows you to represent 1 through 254. But we want to get some negative exponents and some positive exponents, so we divide it in half. 254 divided by 2 is 127. So you shift by 127. So whatever exponent you have up there, you're going to add 127 to it before you convert it. That's the shift idea. So it allows us to represent negative exponents and positive exponents. And again, the reason for that is in binary, if you're using 8 bits, you can represent 0 to 255. We don't allow all zeros and all ones, so that's 1 to 254. 54 and half is 127, so that's what we use for our shift. So you get half of it. Well, one of the exponents is 0, but you get about half of the exponents are negative and half are positive. That's the idea. I mean, the 127 bit's piece is a little bit arbitrary, but you're just trying to get half positive and half negative exponents. That's the idea. Is that what you wanted to see, Lane? Mm-hmm. Okay. It's okay. Lots of questions. I like questions. Again, not this long because of the length of the digits or the length of the numbers, but this is another decent test question to do, being able to convert something over to machine representation. You have to convert to binary. You have to be able to understand how the exponent works, all those things. Okay. Other questions? All right. I'm going to use this to start off an example here of one last thing with machine representation. And then we were going to flip over to polynomial interpolation today. This is what your assignment is over that I just gave you. So one of the ways that you write these numbers a little bit more, or these machine representations a little bit more succinctly, is in blocks of 4. Notice in this case I have should have I must have wrote an extra digit somewhere. I should have 8 blocks of 4. Now I've got 5 on the end unless I. Oh, that's right, because it chopped. Thank you. Right. The last one got chopped. Thank you, Ben. Appreciate that. All right. Notice that we've got each of those in blocks of 4. We can represent each of these with a single hexadecimal or a single base 15 digit. So hexadecimal is base 15. So instead of each place value representing a power of 10 in decimal or a power of 2 in binary, hexadecimal has each digit represents a power of 16. Okay. So in hexadecimal, you need a single digit for the numbers 0 through 15. Okay. Just like when you do powers of 10, right? You need a single digit from 0 to 9 to represent those things. Hexadecimal is the same idea. I need a single digit that represents the numbers from 0 to 15, because then when I get to 16, you would change it to 1, 16, and 0 ones. So that would be 1, 0 in base 16 would give you 16. Okay. Just like 1, 0 in binary is 2. Okay. Same idea. But again, I need a single digit. I can't write 1, 0 to mean 10 anymore. I need a single thing to represent 10. Okay. So the convention for hexadecimal is you use the letters A through F. So base 16A represents 10. B represents 11. C represents 12. Many of you may have already seen hexadecimal, especially if you've had probably computer architecture, but maybe even discrete. A through F represents those single digits. One of my favorite. So you've probably played around with calculators and written different words and with numbers. Possibly. One of my favorite things was I could write new things when I had the hexadecimal letters on a scientific calculator that I had. So I could spell like coffee, for example. See what kind of letters you can use to write different things. Anyway, I was a nerd. It's fine. Still am. It's okay. Anyway, so the idea here is that I can write this a little bit more succinctly if I use hexadecimal, because notice that in a block of 4 for binary, you give the number 0 through 15. All zeros would give you 0. All ones would give you 8 plus 4 plus 2 plus 1, which is 15. Right? So if I want to write this a little bit more succinctly, I can replace each of these with a single hexadecimal digit quickly. Okay? So notice this one is what? This is 4, right? So it would have 4. This is 7. Right? This is 2. And this is all in hexadecimal, by the way. I'm just converting it over to hexadecimal quickly. This is 3. This is 8. I don't have anything big. This is also 8. This is also 8. That's 5. So this machine representation in binary, we can represent quickly in hexadecimal, and I think the book uses brackets around these things. I can do that quickly. They even put a base 16 on there. I was going to pull out another example anyway. But again, we can represent it quickly without having to write out 32 things. I can just write out 8 things. It's a little bit more succinctly to write out and a little bit more succinct to analyze. Yeah, it does put a little base 16 in here. Okay. So one of the things that the book asks you to do is actually work in reverse. It says start with a hexadecimal representation and work back to figure out what number is being represented. Okay, so let's see if we can do that. They've got lots of examples in the book. Looks like they've got about 12 of them to work on. Well, let's see if we can do one here. So, what's it? Sure. Oh, is it 6 instead of 5? Thanks. Yes, it should be 6. Four plus 2 is 6. At least today. Might be in a different class. Might be a different number. It's entirely possible 4 plus 2 might be 1. Happens. First look at me like I'm nuts. It's true. It happens. 4 plus 2 could be 1. Could be 0. Depends on where you're living in. I can come up with 3 different things where 4 plus 2 is 0. Yeah. Okay, great. Don't listen to me. It's fine. Okay. All looking at me like I'm nuts. It's fine. All right. Cool. This is 7C on page 52. Starts with the hexadecimal BF4F 9680, page 16. All right, so we have 8 hexadecimal digits here. That would represent 32 bits. Each hexadecimal digit gives you 4 bits. Okay? So this number that's being represented here is in single precision because you're doing 32 bits. So the idea here is to write out, at least is the way I would think about it, write this out in all 32 bits and parse out the pieces that you need and then figure out what the number is. Okay? So again, when we write it out, we'll have the first bit will be your sign bit, the next 8 will be your exponent, the last 23 is the mantissa part, right? Okay. So now we just need to figure out the binary representation for each of these digits. Well, B is 11. To get 11, I need an 8, a 2, and a 1. That'll be 11. F is 15. That one's easy in binary. It's all ones. 4 ones. 4 is 0, 1, 0, 0. F again is all ones. If you can't do it that quickly, with practice you will, because you're just going from 0 to 15, so it's pretty quick to figure out which one you need. 9 is an 8 and a 1. 6 is a 4 and a 2. 8 is just an 8, and 0 would be zeros. Notice again, you kind of see that I even left it in blocks of 4 here, right? I was writing each one. There was kind of a little space just naturally that I was writing in there. Literally just going through each individual hexadecimal digit, right? Going through each hexadecimal digit and converting it to the binary. Okay. Again, remember, A represents 10, B is 11, C is 12, D is 13, E is 14, F is 15. So yeah, I need to convert each of those to binary. Okay. Next thing we'll do, let's parse it. The first bit is your sign bit. The next 8, 1, 2, 3, 4, 5, 6, 7, 8. There's your exponent. Pardon me. And the rest is on your mantissa. I shouldn't have made that so scribbly, so I can actually see where I'm parsing it right there. Pardon me. Is this number positive or negative? Negative because the first byte's a 1, right? So that's representing a negative number, right? So you tell that right away. I don't need to do any converting with this part, except that remember that what's on the front of this, understood? A 1, right? It's 1 point, all of that, correct? So far we've got 1 point, all of that, and I'm just not going to bother writing the last zeros on the end because those will all just be zeros. Yeah. 1, 0, 0, looks like 5 ones, couple of zeros, 1, 0, 1, 1, 0, 1. Right? Yeah,
how did you know that if the exponent was 8? Is that just single precision?
At single precision, it's 8, right? Yep. The first bit's the sign bit, the next 8 are the exponent, and then the last is the mantis apart. Yep. If it were double precision, you'd have it'd be 1, 11, and 52, which I'm not going to make you do 1, 11, and 52. That's ridiculous. Okay. All right, so right now I know absolutely. Sorry, I also know it's negative. I didn't put that in there. I know absolutely everything except for what the exponent number is, right? Okay. The exponent here is this one. What does this represent? Well, it's 2 plus 4 plus 8 plus 16 plus 32 plus 64. Right? 126. I know it's 126 because of the extra 1 there, it would be 127. So it's 1 less. All right. All right. So 126, though, is the shifted part, right? How do we shift? We always add. So to go back to what the number we need to do at the end is we're going to subtract 127 from that. So what's your exponent going to be in this case? It'd be negative 1, yeah. Okay. So again, this number right here, write that down again. I'll write it below. 0, 1, 1, 1, 1, 1, 1. No, not 0. Yeah, that's right. 2 plus 4 plus 8 plus 16 plus 32 plus 64, right? This is base 2. Is 126, right? Okay. But remember again, the 126 comes about from you had your original exponent and you added 127 to it, right? That's how we put it in machine representation. So to get back to the original exponent, to get this negative 1 here, this is 126 minus 127. All right. All of this is base 2, so I probably should write a sub 2 here, but I mean, you got one bunch of 1s and 0s. And if you're in a class talking about machine representation, you probably assume it's in binary. Okay. What does that negative 1 exponent do to your binary point? If you move it left 1, right? Okay, so first off, notice this is going to be a number that's less than, in absolute value, it'll be less than 1. Oops. So it'll be 0.1100111111 001 base 2. Again, we need to move it 1 place to the left because your exponent was negative, right? And then the last thing we would need to do is convert this to decimal, because that's what the direction's asking us to do, is convert it to decimal. This one represents what? What is this one? In decimal, what does this one represent? A half, right? This represents a quarter, 8th, 16th, a 32nd, a 64th, and so on down the line, right? So this would be, whoa. This would be 2 to the negative 1 plus 2 to the negative 2 plus 2 to the negative 3, 4, 5, 6, 7, 8. Oops, so 2. 9. I think I got all of them, didn't I? 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, and 17. And at that point, calculator computer can tell you what that is. Okay. So again, we're using the fact that every position is a power of 2. They're all negative since we're to the right of the binary point, and I'm just counting. And the ones that appear in the list are where the place values are non-zero, right? They're ones. Okay.
How does the negative play into this answer?
Oh, they should be. I keep forgetting it's there. That's how it plays into the answer. It makes the whole thing negative. I keep forgetting it's there because it's not the important part that we need to talk about. It is negative. Are we okay with how I got those? You want to see one more example like this one? Yes. So 1, 2, that's where those are. Those are zeros. There's the fifth one. So that's where the 5 comes from. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Where it comes from. All right, let's do one more. This is, how about, this is 8D. Oh, I don't want to do 8D. Let's do E. Yeah, I'll do C. Let's do 8C. 8D had things going all the way out to I don't want to write that many decimal places. We have 494F 96A0. Okay, 16. First step again is what? Okay, convert each of your digits to binary, right? 4 is what? Good. 0, 1, 0, 0. 9 is 1, 0, 0, 1. 4 we just said was 0, 1, 0, 0. F is all ones. 9 is 1, 0, 0, 1. 6 is 0, 1, 1, 0. A is 1, 0, 1, 0, and then 0 is the easy one, right? Okay. Everybody okay with getting those single digits converted over to binary? Not too bad. Like I said, with practice, you'll just write them down. Okay. Next step. Yeah, if we split, separate your exponent from your mantissa, right? Here's your sign bit. So the number is positive. 1, 2, 3, 4, 5, 6, 7, 8 exponent, right? The rest is your mantissa part. So for the first part of your scientific notation, then what do we have? Not worrying about the exponent part, but the first part. The 1 point, all that stuff, right? So 1 point, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, and then stop because the rest are zeros. Assuming I wrote them down correctly. So again, remember there was an understood 1 point here, right? We don't need to store that because with numbers represented in scientific notation and binary, that always has to be a 1, right? So there's no point in storing it. Here I'm just writing out the part until I get to zeros. It don't matter anymore. That part okay? Okay. Last part we need is the exponent. So we need to convert this back to decimal, right? Remember, everything's a power of 2, so this is 1, 2, 4, 8, 16, 32, 64, 128. So 128 plus 2, 4, 8, 16 plus 2. So 146. Did I add it right?
Can you do that again? Like just say it out loud.
Sure. So start here with the ones, right? 1, 2, 4, 8, 16, 32, 64, 128. So 128 plus 16 plus 2. If you need to write it out with your exponents, it'd be 2 to the 7th, 2 to the 4th, 2 to the 1st. Eventually, doubling in your head will get more difficult, so you just put it out there. Pardon me. That's again the decimal exponent, but do I want to use this as my exponent? No. What do I need to do? Yeah, subtract 127, which is it gives you 19. Yeah. Okay. So relative to the binary point here, we move it which way? To the right, 19 places, correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. One more, I have an extra 0 there. So 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, because we had that extra 19th spot, right? When I moved it, this right here is only 18 spots. Moving it one more, I gotta fill it with a 0, just like you would in scientific notation, right? I'm sure you've all done scientific notation in science class. It's the same exact concept. We're just doing it with powers of 2 rather than powers of 10. There's nothing special about 10. As a matter of fact, the only thing that's special about 10, that's what's special about 10. That's why we do base 10. Why we do base 10. That's the only thing that's special about 10. There it is. You know what some other cultures use for bases? 5. 8. The spaces between your fingers. Okay. Now there is a culture, I think it's one of the Aboriginal cultures in Australia. It's been a while since I've thought about this stuff. Their counting is 1 too many. Once it gets past 2, screw it. Too many.
That's fair.
That's how they count. Yeah. 1 plus 2, many. I don't care. Many plus many, still many. It's counting really easy. Too many. I don't feel like counting anymore.
I mean, in history of mathematics, we're learning that there was a culture that had base 10 for the tens, but they didn't go to 100. They had a base 60 as a next point.
Oh, yeah.
Carrying over.
Yeah.
So their base wasn't consistent.
Right. Yeah, Babylonians use base 60 as well. Mayans use base 20. Yeah, so lots of fun stuff. Anyway, so this is our number base 2. So the last thing we need to do would be add up all your things, right? So again, this was 2 to the 19th. We know this one already represents 2 to the 19th because it was there, correct? So then plus 2 to the 18th, 17, 16, 2 to the 15th, 14th, 13th, 12th, 11th, 10th, 9th, 8th, and I keep messing up. 7 is 0, 6th, 5th, 4th, 3rd, and to the 1st. Whatever that turns out to be. At that point, like I say, computer or calculator. Is okay? Yeah. Here sounds like a good extra credit problem. I keep giving you throw out ones every once in a while. Write a program that'll go back and forth. Take a decimal number, convert it to the hexadecimal representation, and vice versa. Good extra credit project to do. Right. You don't have to do any of the extra credit ones, but that's a good extra credit one. What's that? It was the one where I sent you the program that converted to binary, and then see if you could take it over to machine representation. This one I would even let you write in something other than R if you want to do it in Python or something else. It's a good extra credit thing to give, you know, practice programming ideas. I don't think it's too bad. More interesting part is parsing it, right? Parsing out the pieces that you need. Any event, any questions on that? Is that okay? All right, cool. Pardon me. All right, so we're going to jump ahead into chapter 4 and talk about polynomial interpolation. It sounds fancy, but all we mean by polynomial interpolation is you're given a set of points, and you want to try to find a polynomial that goes through all of them. Okay. So I'm going to do. This is just. This is section 4.1. All right, so number 1 in the exercises gives you a set of points. X values are 0, 2, 3, and 4. Y values are 7, 11, 28, and 63. Pardon me. The question asks you, actually it says to use a certain technique, but the question asks you to find the polynomial of least degree that goes through those 4 points. So if you think about how you write a polynomial generally, so let's think about it from an algebraic standpoint first to see what we would need for least degree. Okay. And then we'll talk about a couple of different ways about how we'll actually find these polynomials rather than the way you're probably used to. Mainly trying to find something that's a little bit more efficient is the idea. Okay. Everything about what we do in this particular class is to try to solve a problem in a numerical fashion as quickly as possible. Okay? That's the whole goal of everything we do in this course. Find numerical solutions quickly. Those two things are very, very important in industry, right? If you come across a problem in the real world, typically you can't solve it by hand anyway. Typically you need a numeric approximation. So you need to know techniques to be able to find those numeric approximations. And then again, from a computing standpoint, you're typically, if you're working with a real world problem, you're not working with 2 variables or 3 variables. You've got 7,382 variables. So anything that you're computing has to be done fast, right? As efficient as possible. All right. Anyway, back to what I was talking about. So when we have a polynomial, generally speaking, remember that we have a constant term, we have a first degree term, we have a second degree term, and so on up until we have an nth degree term. Right? That's what we mean by a polynomial. Notice that if you have a degree n polynomial, how many coefficients do you need?
N+1.
Yeah, n plus 1, right? So in order to, say, have a second degree polynomial, you would need 3 pieces of information, correct? This is what it means by trying to find a polynomial of least degree. You look at the number of points. The number of points gives you information about finding a coefficient, right? Each piece of information here, each point, gives you a way to find a single coefficient, okay? Since we have 4 points, that allows us to find 4 coefficients. So what degree polynomial are we looking for? 3, right? Because those 4 points will allow you to find 4 coefficients, which means you have a degree 3 polynomial. So in general, whatever list of points it gives you, the degree of the polynomial is going to be 1 less than, well, 1 less than that or maybe smaller. It's possible those coefficients could be 0. It's entirely possible that those 4 points, for example, fall on a parabola. Have the A3 with E0. It's entirely possible that they all fall on a line, and then your A2 and your A3 would be 0. But again, the idea here is each point gives you a way to find a coefficient. Okay? Now think about how you probably have done this in the past. If you've done this in the past, you've probably plugged in the x, got out, and then set it equal to the y, and then solved the system of equations. You're taking linear. You did this in one of the homeworks we did in linear algebra, right? Plug in the x's, get out the y. You got to get the y out, set up a matrix, and row reduce. Okay? That is certainly a method for solving that. You can set up a system of equations. In this case, you would get 4 equations and 4 unknowns. Row reducing, anytime you do Gaussian reduction, though, you get on the order of n cubed operations, where n is the number of equations that you have. That's a lot of operations. So the idea is, can we make this fewer operations? Okay. So again, the first way we do it, the answer is no. It's going to be more operations, but it's very algorithmic versus than having to do Gauss-Jordan reduction if you've done Gaussian elimination before. If you haven't, you can ignore what I just said. The other way is going to be more computationally efficient. But the first way might be a little bit easier to understand from a pedagogical standpoint, so we're going to do that. All right, so let's talk about ignore all of the points and just look at the first 2. Okay? If I'm going to look at these first 2 points here, basically I'm going to be looking for the line between those 2 points, right? But here's the idea that we're going to use to help us figure out the line. And I know you've already figured out how to find equations of lines. Okay? We're going to think about it just a slightly different way and see if we can expand that idea to quadratics and then cubics and any degree that we want. Okay? So here's the idea. I know I have a line. Again, we're just looking for those first 2 points. Here's the idea. I'm going to take the 2 outputs that I know that I want, and I'm going to multiply them by something. Okay? I know when I plug in one of the x values, I want to get 7 out. When I plug in the other x value, I want to get 11 out. Okay? So that's why I've got the 7 and the 11 there. In particular, when I want to put 0 in here into the polynomial, what do you think you want this coefficient to be? And what do you think you want this coefficient to be if I put 0 in this case? Yeah, I want 1 here and 0 there, correct? I want a 1 coefficient, so I get 1 times 7 when I plug in 0. I want a 0 coefficient, so that I get 0 times 11 here. Other way around, what do you think I want for the coefficients if I plug in a 2? Yeah, I want a 0 here and a 1 there, right? Same idea, correct? Okay. So the way we can do this, and I'm going to write it out a little bit longhand so that we can see what's going on. I want to make a fraction. On bottom, I'm going to divide out by 2 minus 0. The idea here behind this is that when I plug in one of the numbers, again, we want to get a 1 out. I want to scale it. Does that make sense? I want to scale it to a 1. When I plug in the other number, I'm going to get a 0. Okay? So this 2 minus 0 piece here is just scaling things so that when I plug something in, I'm going to divide out by that quantity. Right? It's a lot easier to plug in, say, a 2 for x and get a 2 on top than it is to plug in a 2 for x and figure out some other number to put in there, right? So I'm using this number on bottom to scale. Okay. Again, you said you wanted what here? You want 1 here and 0 here when we plug in 0, right? So let's think about how we can do that. If I want 1 here, I can use what? The x minus the 2 here? Or the other way around. The 2 minus the x here. Right? When I put 0 in for that, I'll get, right, 1 here. Same time, what do I need to plug in over here to get? So what do we get? A 0 when we plug in 0 and a 1 when we plug in 2? Yeah, just an x I think will work here, right? We agree with that? I probably should have written my numbers the other way around, but this is the concept, right? When I put in 0 here, now I've got the exact same thing on top and bottom, don't I? You know, when I put in 0 here, it kills the whole thing. When I put in 2 here, that gives me 0 on this one. When I put in 2 here, it gives me a 1 there. Right? So generally speaking, what could we have done? Let's say we had, let's just say we had a general idea here. Let's say we had x naught and x1, and then we had y naught and y1. Let's see if we can extend this. And again, we're just doing this for lines. We're just doing this for lines, and then we will extend it to higher degree polynomials. The reason why I had to do the 2 minus x up here is because I reversed my order a little bit, didn't I? Okay. So one of the things we could put on, again, the idea here is to, I want a y naught and a y1. Bottom on the scale, let's do an x naught minus x1. I'll do it in the other order. I did 2 minus 0 in the other case. Let's do 0 minus the other. I need, obviously, x's that we're replacing. So let's do x minus on top on both of them. Again, when we plug in x naught here, I want to get a 1 and a 0 because I want y naught out, right? When I plug in x1, I want to get 0 and 1. Okay? So let's think about when we want to get the zeros. If I want to get a 0 when I plug in x naught, what better I subtract from x? X naught, right? Here? We agree? If I want this one to go away when we plug in x naught, I better put in x naught here, correct? Okay. If I want to, whoops, does that make it correct when we put in, why is the number backward? No, this should be x1. I'm going to do it backward here. This should be x1 and x naught. Make everything come out to be nice. Sorry, I want to make sure my signs are correct. Over here, same idea. When you plug in x1, you want this to go away. Should be x1. Just need to make sure my signs are adjusted correctly. Okay. So notice again here what we're doing. I'm working with the first point that we have, right? And then I've got x naught minus x1. Here we're doing the second point that we have. I'm doing x1 minus x naught on bottom. Okay. Can we extend it to 3 points? And then can we see what's going on generally? Let's say we have x naught, x1, x2. And we have y naught, y1, y2. Same concept. Something times y naught. Something times y1. Oops. Probably need a little bit more space than what I'm leaving myself here. It's okay. We'll figure it out. Something times y1. Y1. and then something times y2. I didn't realize your sweatshirt had a tail. That's fantastic.
There's also here's on the hood.
Oh, awesome. I love it. Just caught my attention as you got up. Sorry. It's fantastic. All right. What do you want your coefficients to be when you plug in x naught? 1, 0, 0, right? When we put in x1, we want 0, 1, 0. When we plug in x2, we want 0, 0, 0, 1, right? Okay. All right. In particular, if I want to make sure that this one's not 0 when I plug in x0, and then I want zeros for the other ones, what do you think my numerator should be? I want to make sure that it's 0 when you plug in x1, and it's 0 when you plug in x2. What do you think your numerator should be? Yeah, you should probably have an x minus x1 and an x minus x2, right? We agree with that? So we'll worry about the denominator in a second. We're going to make the denominators match so we get ones. But I want this one to be 0 when I plug in the other points, right? What should your numerator be for the next one? Yep, and... Yeah, good. Now I want x minus x naught and x minus x2, right? I want those to be zeros, right? We agree? And then the last one? Good. All right, so notice that your x's that are appearing, your x sub whatevers that are appearing are the ones that aren't associated with the y value, right? Y naught is got an x1 and an x2. Y1 has an x naught and an x2, and so on up the line. Yeah? Okay. Now we need to scale, right? When you plug in x naught, you want this first coefficient to be 1, right? So what do we need to divide by? Good. Yeah, when I plug in x naught, I want those terms to go away, don't I? So x naught minus x1, x naught minus x2. For the next one, we want this to be a 1 when we plug in x1. What does your denominator need to be? Good. Finally, the last one.
x2 minus x naught, x2 minus x1.
Good. Fantastic. Good. Do you think you could extend this to higher degree terms? Yeah. Okay. So let's go back to the data that we had. Scroll back up here. This was the data, right? I'm going to write it back down so we see what we had for the form. 7, 11, 28, 63. Let's see if I can remember that. 7, 11, 28, 63, 0, 2, 3, 4. I did remember all the numbers. All right. Pardon me. Let me move it a little bit. Okay. We got 4 outputs, so I'm going to need 4 terms, right? Make sure I had enough room to write everything. I wrote it on 2 lines. Okay. Write it however you want, but I just make sure that when we fill these things in, I wanted to make sure I had enough room. Right to the right of all the multiplication symbols in there, what numbers do I want to put in there? Good, yeah, the outputs, right? The 7, 11, the 28, and the 63, correct? We agree with that? Okay. The other ones are going to be fractions. The coefficients will be fractions, so we'll go ahead and put the bars in there. Let's do the numerators first, and then we'll figure out the denominator, right? Okay. for 7, let's think about the other values, right? For 7, I want this coefficient to be 0 when we plug in what? Well, I want it to be 0 when we plug in the other ones, right? The 2, 3, and the 4. I want it to be 1 when I plug in 0, right? I want it to be 0 for the other ones. If I want it to be 0 when it's 2, and 0 when it's 3, and 0 when it's 4, what does the numerator need to be? Good. Back in algebra class, you've probably created polynomials where they have zeros at certain places. That's what we're doing, right? I'm creating a polynomial that has a 0 at 2, at 3, at 4, right? Okay. What about at 11? I want it to be 0 when?
0, 3, and 4.
Okay, so what do I need to put on top?
X minus 0.
Yeah, I'll write it as x minus 0, so I can just have an x. That's good. And the next ones? Good. Yeah, exactly right. Yep. The other ones are going to be good. It'd be x minus 4. Good. Yep. And the last one will be yep. Good. Are we all okay with where I'm getting those factors from? Is okay? Cool. Notice again, I'm just thinking about how do I make it 0, right? Okay. All right. Then we needed the denominators are, I want to scale things so that we get a 1, right? When I plug in 0, I want 1. So what do I need to divide by?
0 minus 3, 0 minus 3, 0 minus 4.
Good. All right, just plug in the 0 for the x, what you just wrote on the top, right? The next one will be
2 minus 0, 2 minus 3, 2 minus 4.
good. This one will be
3 minus 0, 3 minus 2, 3 minus 4.
good. And the last one?
4 minus 0, 4 minus 2, and 4 minus 3.
Fantastic. Yep. Oops. Yeah, that's exactly right. Then, of course, we could simplify it, but that's it. That's how you do that. Okay. All right. So these polynomials that we're finding have special names. These are what are referred to as are called cardinal polynomials. They're actually called the Lagrange cardinal polynomials. Okay. The way you make these polynomials, if you want a general formula, I just think it's easier to go through it algorithmically than try to do it from the general formula each time. But notice that you do a big long product of things, right? Okay, so the way the product works, and then we're just talking about the coefficients here, right? So when you write, usually we use an L sub I of x. We use a little L sub I of x. It's a big product. You know how you use a sigma for a big long sum? You use a big capital pi for a big long product. The product will do a different index. J will go from 0 to n, but I don't want the indices to match. So that's the notation we'll use. Notice that we're trying to get this degree 3 polynomial. We have 4 terms that we're creating, but only each time we're doing a product of 3 things, right? Notice that we never take x naught minus itself or x1 minus itself, right? So that's why this is j not equal to I piece here. Okay. And then the product we do is on top, we take your x minus x sub j, and on bottom, I don't know why I put parentheses around that. Doesn't matter. And on bottom, you do x sub I minus x sub j. I'm going to take those parentheses off, as a matter of fact, because I don't like it. These are your coefficients, right? Those are the coefficients we created. Okay. Again, Does that look like a really nice formula to try to remember? I think it makes more sense to try to remember the algorithm, correct? Right? But this is the formula for the Lagrange cardinal polynomials. So then you can write your interpolating polynomials. So this is the Lagrange form of the interpolating polynomial. Oops. And this is exactly what we did. You took your polynomial (0 to n). You took your Lagrange cardinal polynomial times whatever the function value was at that x sub I. All right, that was how we did the coefficients times the values, correct? The outputs. Okay. So this is the Lagrange form of the interpolating polynomial. Computationally, this isn't exceptionally nice because, again, we've got lots of products that we have to do it. Conceptually, though, it's really nice, right? How did we create it? We said, I want the coefficient to be 1 here and 0 everywhere else for those outputs, right? So from a conceptual standpoint, this is a really nice thought of how we can do these polynomials, right? And it always works. So all that stuff that you do when you've solved systems of equations to find a polynomial, you can ignore that now and just do this algorithmically, right? You don't have to go through and solve a big long system of things. You can just create the polynomial as you go. Now, it doesn't necessarily look like the nice form of a polynomial, right? Because you've got all these products, but it works. It is a polynomial. It has to be the same polynomial because, again, if you have a polynomial that goes through n plus 1 points, that's it. It's the only polynomial that does it of degree n. Okay. When you have a polynomial of degree n, it has those n roots. If you had two different polynomials and subtract them, you'd have a polynomial that had more roots than it has degree. And you'd have an issue. Or it has to be the 0 polynomial, which is why they have to be unique. Okay. So again, this gives you a way to compute it that, like I said, you don't have to solve anything. You don't really have to think, right? You can just algorithmically chug through it and get it. Okay. All right. So that's the Lagrange form. What we're going to talk about next time is doing Newton form and doing what we refer to as divided differences, and I don't have enough time to get into it, so I'm not going to even try in 4 minutes. Okay? We spent more time on the binary stuff and machine representation than I thought. So we'll get into this on Thursday. Okay. But again, we'll have another algorithmic way to do this. So we don't have to set up a system of equations and solve the system of equations. We have an algorithm that will produce the polynomial that we want. And when we're doing the divided differences method, it'll be with fewer computations than you would have done Gauss-Jordan reduction, which is nice. All right. Talk to you on Thursday. Have a good one.
Let me ask real quick. What would be the criteria for yes or no?
What do you mean?
You mentioned that you might have been Joe.
No, go Joe. If I say it's extra credit, it's extra credit.
I'm trying to figure out what the criteria was. The binary to hex. Was it regarding single point precision exactly?
There's just single precision, machine representation. Yep. Write the code that would do it back and forth. Yeah.
Oh, no, the other one you mentioned in class or
Oh, the binary one, that was the one I sent in the email? Or the one I sent today or the one in the email?
the one you just mentioned today.
The one I just mentioned today was if you've got the hexadecimal representation, convert it to decimal and vice versa.
Of a single point precision or just any number? Whoa.
You should have single precision hexadecimal representation converted to decimal.
Okay.
Decimal number converted to machine representation in hexadecimal.
Okay.
Yeah, that's what I'm saying. Be able to go both ways.
Okay. Got it.
Got it.
Two questions.
Yeah.
Number one, can I use your paper clip?
Oh, I just set it on there. I'll staple it when I get done with this. Yep.
Huh?
Did you get an
Number two.
assignment?
No, I did not.
We actually have something to talk about this time.
I'm curious about, you said 4 plus 2 could equal 0, and you said there were like 3 instances.
Yeah.
Where could that happen?
So the easiest way is one of the algebraic structures that you can create is it's called modular arithmetic, where you basically look at a number and then divide it out and just look at the remainders. So if I do remainders by 2, it would have 4 plus 2 is 6, remainder but divided by 2 is 0. I could also do it by 3 or by 6. And all of
Okay.
those would have a remainder of 0. So 4 plus 2 is 0 in those 3 different structures.
Interesting.
Yeah. I do algebra, abstract algebra is what I do as a research area, so that is of interest to me.
Yeah.